Hi guys, I'm Mike. Let me get the presentation going one moment. Great, that's our wonderful logo from Cryptonomic. And my name is Mike. I work at Cryptonomic. We work on various blockchain things. I'd like to thank Tezos India for inviting me here today. I'm always excited to do presentations like this for hackathons and things of that nature because it really allows me to get this excitement from you guys about the wonderful things that are possible with blockchains. Because I've been working in this space for some number of years now, and it's always really great to see new ideas come in. Right. So I work with Cryptonomic on a bunch of blockchain stuff. A lot of the publicly visible work that we do is for Tezos. Prior to that, I have extensive experience in enterprise finance with Bear Stearns, their predecessors and their successors. This is the second talk that I'm doing for this event. There's one more coming up, and this is going to be about contract composition in SmartPy. But before that, let's talk a little bit about us from Cryptonomic. We are an independent company. We're dedicated to these hard to pronounce words and even harder concepts. These concepts are slightly more difficult if you've been paying attention to the news out of the US this week. We're blockchain agnostic in general, but today, of course, is all about Tezos. Fundamentally, we as a company want to make blockchains more popular and more useful. And to that end, we create development tools, we build products, we create a lot of documentation, and we host events like this. We are a small team in Brooklyn. We recently returned to the office, and it was very exciting to see that the neighborhood hipster cred has survived the pandemic. As a team, we have broad financial experience, but we've also built high availability systems, high complexity systems in other industries. Yes, so let's talk a little bit about what exactly we've done on Tezos. I like to think that we bring discipline of experience to Tezos because we've delivered so much software over the years in general. Since inception, we've built developer tools for blockchains and infrastructure to run these blockchains. And we've created a lot of documentation for how this could be reproduced by other people. So to that end, we have the Galleon wallet. This is one of our most popular products. This is a wallet for Tezos, and it has support for lots of the popular DeFi and NFT projects out on the platform now. We have a mobile wallet, Galleon Mobile. This is a screenshot of the current release. We have one coming out soon, which is a lot more exciting. I don't really want to spoil that surprise. And I think I said the same thing last week. But I got to say, whenever you talk about dates in software delivery, you jinx yourself, and it adds 3 weeks to whatever you said you were going to do. This is Aranex. It's our analytics and data reporting tool for blockchains. I use this myself for development purposes quite a bit, in addition to just reporting on financial transactions that happen on Tezos. The report you're looking at gives me contract invocations that ended in an error subject to certain criteria. So this is since July 22nd. These are transactions, failed transactions, and destination starts with KT1. As you know, smart contracts on Tezos, smart contract addresses start with KT1. So that's why we're looking at that. So Aranex is interesting to me personally because of my financial background in financial reporting. The thinking was always that blockchains need easily accessible tools to become more mainstream. So we built Aranex for that. Finally, Nautilus Cloud. So blockchain infrastructure is difficult. so difficult. There was a protocol upgrade on Tezos a couple of days ago. The network is still a little bit in flux, although it's settling. I would highly recommend that you do not run your own blockchain infrastructure. I mean, unless this is the project that you are actually working on. It is time consuming, and I would rather have someone else do it. For that matter, at Cryptonomic, I don't do infrastructure, but I do use the service, of course, and you might use it as part of your project as well. All you need is a GitHub account. So you can create a login, and there is a free tier that you can use to connect to Tezos nodes and the Consei indexer nodes as well. Right, so these are the things that we built for Tezos. And they're built on top of Consei, which I just mentioned, which is an indexer written in Scala, and Consei.js, which is a JavaScript library that we use for front ends, for all the front ends that you've seen. So Galleon on desktop is written with Consei.js. It uses it to interact with both blockchain nodes on Tezos and with indexer nodes for Consei. Same is true of Aranex, of course, and Galleon Mobile. So these are for React. We use them in React, React Native, on the web, everything in between. Cool. So as I said, presenting these workshops is really inspirational. I can't wait to see you guys turn a pile of cryptographically enabled code into actual product demos. And that's really important to remember, is that blockchains are at this point mature enough that you can really build something user-facing, something easy to use, potentially something that people will be excited to use themselves. And of course, technology matters, but I'm excited about applications of this technology more than I'm excited to see more plumbing. Plumbing we build so that we can have exciting products. So before we start, it's important to remember that blockchains are intrinsically open source. So you can learn from the mistakes that people have made. You can learn from your own failures. You saw Aranex, I was specifically showing failed contract invocations. But you can also learn from other people's mistakes. You can see how other people solve problems that you may potentially encounter as well. In addition to learning from their mistakes, you can get inspired by other projects. You can see how other people are solving problems that are perhaps similar to yours. You can see how they structured not just their projects in terms of code, but how they structure their broader product architecture on blockchains. And that's important. And of course, you can use Aranex for some of this. And it's important to not start from scratch, right? So already I mentioned Nautilus Cloud. You can leverage that as part of your project. You can look at numerous examples of the SmartPy tool that we're about to use. It's also important to ask questions, right? So I'm available. There's a very active community for Tezos on Twitter, on Reddit, in other places. So if you come across a problem that you think others may have faced, ask. You're bound to find someone who will be very excited to help you. Finally, this can't be stressed enough. Once you write your contracts, it is so important to be testing. And that's why we like to use SmartPy, because not only is it a simple syntax for smart contract development, it also has an integrated simulation engine, so you can test all the edge cases that your smart contract may have. So I would expect that, and this is true of our own contracts, that a smart contract you write will have a lot more code dedicated to testing it, to testing state transitions, to testing different types of operations that a user may run, than the smart code I'm sorry, smart contract code itself. And with SmartPy, you can do this before you deploy the code to even a testnet, and that's really cool. We'll see some of that as we write our smart contract today. Right, so let's quickly cover Tezos and how it's different and interesting. My understanding is that at least some of you already know a bit about the platform. What's Tezos about? So liquid proof of stake, very cool stuff, very different from a bunch of other proof of stake implementations where user balances are always under user control. They're never locked. They can always be spent. Delegation is part of the on-chain governance process, which we just had a successful transition between protocols again. That's really incredible. I mean, it wasn't without hiccups, certainly, but the point is that the entire chain transitioned towards a new protocol that has new features. And this, despite some infrastructure problems that we faced in the first couple of days, this was a very smooth transition conceptually. We got new stuff and everyone agreed that this stuff is a good idea. And the whole chain went, and there's no hard fork, if you will. Smart contracts on Tezos are also different. They're strongly typed out of the gate, which is great. And this, the way they're written, enables formal verification. One thing to think about is continuation passing style and the way that impacts your inter-contract calls. So definitely read about that. Oh, yes, and another important thing. So the protocol upgrade that we had a couple of days ago changed various things about the platform, but the one we had before that was more interesting to me, at least. And the reason is that it dramatically changed the way smart contracts were implemented on Tezos. So it just shows you the power of this platform where core functionality can change protocol to protocol and new things can be added. So what happened in Florence, the Florence upgrade, they're named after ancient cities. So the most recent one was Granada, they're alphabetical. Contract invocation style changed from breadth first to depth first, which has implications, of course, for the way you manage state internally. But it also makes it a lot easier to think about how contracts are invoked. And this was a feature that was added years after the chain originally was launched, which is pretty impressive. Right, so let's talk about actual smart contracts and how they're written. There are several interaction patterns with a smart contract. A user may simply ping the contract. What I mean by that is a blockchain, first and foremost, is a ledger. It's a ordered list of transactions, right? And if someone calls a smart contract, the invocation itself is recorded, and it's recorded permanently on chain, and you can reference this invocation later. For example, we were looking at, again, at invocations on Aranex. So there is value to be gained from writing smart contracts that don't actually necessarily have any logic internally. So because you can simply use a block explorer or a reporting tool to see how users interact with the contract. So one simple example would be is if you wanted to run a simple online poll, you could ask people to invoke a contract with a collection of parameters, voting, let's say, left or right. And these votes would be recorded as contract calls. Even though the contract itself has no logic internally to tally these votes, because the parameters are different, you can tally the votes later in the block explorer. You can invoke a contract, meaning that you can send in parameters, and these parameters will somehow change the state of the contract. So one simple example, or perhaps a complex example, is an automated market maker like Plenty is releasing soon, for example. Their people send in parameters, the state changes, the blockchain state somewhere else may change. For example, token balances get adjusted. So that's invoking a contract. You can fund the contract. What I mean by that is it is entirely possible to send contract parameters without sending any balance to a contract, right? But you can also, of course, send balance. So if you were using an AMM and you wanted to exchange the coin, in this case XTZ, for tokens like USDTC, you would send an XTZ, you get back USDTC. Finally, sequencing. And what I mean here is that you can call multiple contracts at the same time, or perhaps the contracts themselves will internally call other contracts. One really interesting thing about Tezos is there's a concept of operation group. And what happens is the operation group succeeds or fails atomically. And this is really, really cool. So for example, I can call one contract to approve a token balance, since we're talking about AMMs. So let's say I'm going to exchange a token for Tezos. So before this AMM contract, automated market maker contract, can act on my behalf to take my token balance away, I have to approve this contract to my token balance. So I will call the approve function. Then next I will call the AMM function to say, I would like to exchange one ETH for XTZ, and I expect to get back, let's say, some amount of XTZ in return. This approval and the subsequent AMM call go into the same group, and they succeed or fail together. So if, for example, I don't have sufficient balance to approve, perhaps the smart contract call fails, and then subsequently the AMM call doesn't even get executed because the call before it failed. So that's really, really useful. And it's good to think about how you might build your smart contract architecture such that you split them into different parts so that they're easier to maintain. I mean, smart contract development in general is just like any other software development. There are good practices that you can apply to smart contracts that you would apply to other software. Cool. So in general, smart contracts are permanently deployed. What I mean by that is the code that you assign to a particular contract address will always be that. There's an asterisk. We'll talk about why that is in a minute. Privileged access. Tezos doesn't provide a platform level manager for a contract, which means that if you have privileged operations, you have to have an access control system of some sort in place, and you have to write it yourself. It's not hard, and we're going to do that in our example today. The idea is that if you have a single manager, you basically have to check up front whether or not the contract call is coming from the account that is considered to be the manager. And for that matter, you can make the manager a multi-sig contract, meaning that you could still have multiple parties agree in an action before the action is taken in the contract from a management perspective. And the other thing to keep in mind is that we're developers, we may write and deploy contracts, but other people may be responsible for maintaining them in production. What that means is you will likely need to provide a method for changing the administrator. So I might deploy a contract. Let's say Ohm is going to be managing this contract going forward, then I'll deploy the contract and I'll call the function to switch the manager address from mine to his when deployment is done. Unspendable funds. Smart contracts on Tezos intrinsically do not have the ability to transfer funds unless you implement this functionality. So this is important because there may be cases where people perhaps accidentally send money to your smart contract, or perhaps they accidentally send a token balance to your smart contract, and it may be useful to provide functions for rescuing these funds, so to speak, or to at least move them, even if you don't necessarily send them back to the users. Whitelisting. So similar to administrator access, you may perhaps want to limit smart contract functionality to just the users you want to approve. So if you have, let's say, a club of some sort that there's a bunch of you guys meet in a coffee shop every week and whatnot, and there's some smart contract that you would like to use, and you may want to restrict the smart contract not just for admin access, but for user access to a specific set of users, and you might want to implement a whitelist for them. And finally, state rescue. This is related to the first bullet, really, and sometimes, in addition to this unspendable funds issue where people may send you money to the contract accidentally, there may just be other things that happen that you did not originally account for. And what Tezos has available to you as a tool for this is you can execute arbitrary code as part of a smart contract call, if you implement that functionality into your smart contract. Now, for me, that's controversial potentially because smart contracts should be auditable. I personally am very careful about using smart contracts that have functionality that allows for this sort of dynamic code execution. And we'll cover that more about that later. But the idea is that as much as the contract as deployed always stays the same, there is a way to provide functionality that allows it to execute other code that wasn't originally written in the contract. Other things to think about. Input validation. That's an interesting topic for me, right? So smart contract calls cost money, right? You have to pay a fee to execute a contract, and this fee is generally proportional to the computational complexity of the contract, right? So you incentivize the validator, the baker, on Tezos to include the operation in the block, and you pay them money to do this. So input validation would be logic in the contract, which means it adds computational complexity, right? Which means it increases the cost of calling a contract. So perhaps if calling a contract with invalid parameters will always result in a failure without prior validation, maybe you don't validate so much input. I mean, this is not necessarily a high cost, but it is nonetheless a cost, and it's something to think about when you're writing smart contracts. Storage. Storage is quite expensive on chain. So there are three kinds of storage on Tezos. First, there is the chain itself. It's a ledger. And when you submit an operation to the node, the cost of the operation includes in it the storage cost of actually just keeping that record on the chain, the record of the application itself. That's cheap. It's cheap, but it's also not internally useful, meaning at the moment, at least, smart contracts cannot interrogate the history of the chain. So you can't say, hey, what happened in block, -10 from right now. Then there is storage in the immediate contract state, and that has a cost. And then there's storage in something called big maps. So there is a way for you to store potentially large objects or larger objects anyway on chain in a hash table like structure. But these things have costs associated with them. Another thing to think about are fractions. So floating point math isn't natively supported on chains because floating point numbers are represented differently in different architectures, and you have to have deterministic results for blockchains to work cryptographically. So what happens is everything is an int. And if you would like to support floating point math, it's usually fixed point. So let's say I have a token contract and the token has 8 decimals, right? So that means that, let's go with 6 decimals. 6 decimals. So that means that one whole token is actually represented on chain as 1 million. Now imagine you have 36 decimals, right? So then it's a very large number, which is fine. as far as math and storage goes, but it's something you need to think about how you write your interaction code in, let's say, JavaScript, because JavaScript doesn't natively handle 36 decimal place floating point numbers. And of course, internally, when you write smart contracts, you have to consider the fact that if you're exchanging tokens, that one token may have 6 decimal places, another one may have 36 decimal places. Finally, external state. So you are probably aware of the concept of oracles. It's important to think about how much trust you put into Oracle data, because you can query an Oracle, but you don't have any control over when the Oracle might get updated relative to the actual state of the world. You don't have any control over how the outside state might change before the Oracle is updated. So these are definitely things to think about. Finally, loose immutability. So I mentioned this earlier, arbitrary code execution in a smart contract code. It's also possible to store a Lambda. Now, this effectively enables upgradable contracts. What I mean by that is you can write a function and deploy it as part of a contract, and that's that. Or you can write a function that says, well, get the actual function payload from this place in storage and then run that. And then you can have another method that says, well, update this function to a different logic. So this sounds cool, but it removes a critical aspect of trust on chain, because now all of a sudden smart contracts that were deployed a year ago can have different functionality later. And then this functionality can change in between the calls that you're making. So you may look at a contract at T0, like right now, and audit the function and gain a level of comfort that this function perhaps behaves as you expect it to. And then at T1, well, let's say T2, you call this function, but it so happened that someone updated the function at T1. So you will get a result that's unexpected relative to your audit at T0. So that's definitely a consideration. Cool. So today, we're going to talk about a simple smart contract, and DAOs are popular these days. So let's build a DAO. It'll be a single contract. It will distribute tokens. Users of the DAO will be able to create proposals and vote on these proposals. So let's do that. Excellent. I think you guys can see my screen. And this is SmartPy. The native language on Tezos is Michelson. Michelson is a stack-based, type-safe language with syntax similar to assembly, which is perhaps not the most user-friendly thing to use, nor is it the easiest thing to think about, because most people don't write in stack-based programming languages. SmartPy helps because not only does it have Python-style syntax, it also has Python-style constructs, and you can essentially have object structure that you already used to in object-oriented programming. You can have functions and reusable code and so on, even though underneath, when all this is run, it gets converted into a Michelson smart contract with, obviously, it's stack-based and so forth. So, pardon me. A few things that you have to do that are SmartPy specific. We're going to import, and keep in mind, this is a Python program, right? So this actually runs as Python. That's really cool. And the other thing that the SmartPy guys do is they compile the native libraries for Tezos, which are written in OCaml, to be able to run these simulations that we'll talk about in a minute. Let's actually clear the output. Excellent. Okay, so There's, again, some standard structure. We're going to have a name DAO. It's going to be a smart contract. There is lots of help written by these guys. It's available under the help button. There's a syntax reference. There's a reference for all the special types and so forth. We'll initialize this contract. We're going to give it 2 parameters, a name and settings. Now, it might be an odd choice, if you think about it, to use SmartPy for smart contract composition that ends up being type safe, whereas SmartPy, of course, is not. So the way SmartPy solves this problem is they infer types, and they do so in 2 ways. Either you explicitly specify the thing that you're going to be recording and using. So here, this is an explicit type definition. So this is incidentally a big map that I mentioned earlier. So we're going to have a hash table. Key is going to be type address, and the value is going to be a complex type, which will contain a tuple of 3 elements, which is going to be an int, another int, and a third int. The other way SmartPy infers types is through tests. So, for example, you see here, I say that name equals name parameter, and I don't specify what type it is. Later, when we look at the tests, you will see that name is a string. So SmartPy will recognize that from the tests and label name as a string later. Cool. Same with settings, and settings is going to be a complex type. Now, this is an interesting function right here. So first of all, you can have several kinds of functions in SmartPy. This one is an entry point. An entry point is a method that's externally callable in a smart contract. So default also is a special type of method. I'm sorry, you guys want to see larger text. Let me zoom in. Okay, I hope that's better. So, yes, default. So it's possible to call a smart contract without explicitly naming a function. This is important for contracts that expect to receive balances, meaning that someone may transfer a coin balance into the contract. This is especially important on Tezos because accounts that carry a balance should be delegated as part of the governance process on the platform. So we need to explicitly allow for this to happen. Now, here, we were talking earlier about how people may accidentally send you money and you don't want to have it. So what we're doing here is we immediately send it back. So sp.send is a representation of a balance transfer in Michelson. And what we're saying is send to the caller of the contract the amount they just sent in. So we immediately refund. So what are we actually going to refund? We're going to refund the balance that they sent in. We're not refunding the fee. Transaction fees are, of course, taken by the validator, and there's no control that the contract itself has over those fees. Cool. So this is a DAO. What that means is we will have a governance process that people will participate in, and generally speaking, that happens via tokens. Now, it's important to remember that this is a really simple example that I'm trying to cover with you guys, like front to back in a span of an hour. So this is not good contract design. It's a demo. So if I was thinking about writing a DAO properly, so to speak, I would do so in a modular fashion. So there would be a DAO contract. There would be a multi-sig contract to manage the DAO contract. There would be an external token contract. And why would you want to do that? So it's conceivable that the DAO itself may change over time, but the token is unlikely to change, right? A token is conceptually really simple smart contract. It's a ledger. It keeps a list of account to balance. That's it. So having that functionality be external to the DAO itself makes a lot of sense. And again, we were talking about validation of input. So here we check if the amount we're receiving is greater than 0, because we're going to issue tokens based on the size of the deposit. And we're going to issue 1 token for every microtez. So Tezos has 6 decimal places as a coin. So 1 microtez is going to be, in this case, 1 token, simply because the math is easier that way. So do you need to do this? Check for invalid amount. Well, let's see what happens next. We increment the deposits that we received. We create a token amount that we're going to assign to the sender, and then we store it in the balance table, which, this is functionality right here that would be in the token contract normally. In a more sophisticated DAO, this would still occur. This would be a call to the token contract externally. So let's say this line wasn't there. What would happen? We would increment the deposits by 0. We would issue 0 tokens and then assign 0 tokens to a sender. So they're still spending fees to execute this operation, even though the operation effectively results in nothing. But if you call this contract properly, this line still gets executed. Is it necessary? It's up to you. One really useful thing is this message parameter here. So you're actually going to see invalid amount in the error message that you get on chain, and that's really useful. It's also relatively expensive. What I mean by that is smart contracts, strings are relatively large. So you might instead use something like 1. And then in your documentation somewhere online, you will say that if you receive error 1, it actually means invalid amount in the context of the deposit operation, perhaps. So you definitely have options there. So similarly to the mint operation, we have an burn analog, which would be a refund. Again, it's an entry point, and essentially says, I would like to return my tokens and get back my Tezos deposit. Now, again, simple example, but why did I make these decisions? For a governance process of any sort to make sense, to function properly on a blockchain, because keep in mind, blockchains are adversarial environments, right? A smart contract you write will be tested by blockchain participants for errors in logic. People will look for a way to exploit your contract, perhaps for financial gain, or maybe just to screw with you, because why not? So a DAO that we're building will allow people to make proposals and vote on these proposals. But you have to be a token holder. And to gain these tokens, you have to deposit Tezos, you have to deposit the coins. So what we're doing is we are forcing people to stake something of value. And the idea here is to discourage malicious behavior. Transfer, this would be another operation of a token. We are excluding transfer from this simple example. Transfer, in terms of DAOs, transfer of tokens is an interesting thing critical thing really to think about, because it depends on how you're going to be tallying the votes. So this is type of attack on DAOs, which is a flash loan attack. The idea is that in a single operation, and remember I said that operations on Tezos, operation groups are atomic. So in a single operation, I may be able to buy or borrow tokens required for this DAO to vote on a proposal or submit a proposal, and then sell these tokens immediately. Now, this token is non-transferable, so you can't have a borrow function because these tokens can't be listed on an exchange. But presumably, real life DAOs would have this functionality, and flash loan attacks is something you have to think about. Cool. So as I said earlier, really simple thing. We're going to allow people to propose things. What are we proposing? We're going to be proposing a new name for the DAO. So the DAO is going to start with a particular name. Then people will deposit XTZ to gain tokens to propose a new name. So now, how do we do this? We're going to do a bunch of checks. First of all, does the sender of the name change proposal have a balance of these tokens? So this is the stake issue. We want people to have a vested interest in this. Is the amount of their stake larger than some settings? And remember I said earlier that types are inferred. So now all of a sudden, we're adding an element to our settings structure, which was not explicitly defined above. So proposal stake, some number, and is the user balance above that threshold? Another thing, proposal expiration. So in this example, we're only allowing a single proposal at a time. So the question is there an active proposal? Because if so, we should not allow people to propose a new one. And finally, is the proposed name the same as the current name? And if yes, then we fail the operation. Why do we do this? It's possible that users may want to spam the DAO with spurious requests just because they want to be malicious about it. And maybe they send in the same name, thereby clogging the process, which means that as long as there's an active proposal, a new one can't be recorded. So we're saying that if the name is unchanged, then don't allow the proposal to go through. And finally, we record the proposal as the active one, and that's it. Oh yes, and the expiration is in terms of levels. So relatively recently, Tezos added this functionality through a different protocol upgrade that allows smart contracts to know which block level they're at. That's pretty cool. Tezos also has the concept of time. So you can actually create financial type instruments that are time-based. So lots of people are used to savings accounts that pay interest on a regular time schedule, like in terms of days or months or weeks. And you can do this on Tezos natively, which is really cool. You don't have to estimate what time it is based on some other external factors. You can just say, what time is it? And of course, it's not going to be particularly accurate to the millisecond or whatnot, but it's good enough for things like interest accrual. But the other thing that you can do here with Level is you can create financial instruments that are blockchain native, where time passes in terms of blocks rather than seconds. So you can accrue interest every block, regardless of how long in terms of seconds or minutes it actually takes. And speaking of block time, that's one of the things that changed in the most recent protocol upgrade. The block time went from 30 seconds, I'm sorry, from 60 seconds to 30 seconds. There's some conditions around that, but generally speaking, we now expect blocks to take 30 seconds on average instead of a minute. Cool, so we're almost there. What else do we have left for DAO? We have to be able to vote. And voting is really the same thing. We check to see if the user has any number of tokens, and we check to see if the current proposal has expired. Finally, we expect the user to say yeah or something else, and we'll see what the something else is further in tests. And all we do is we say that the particular user has voted with their balance, and they voted +1 or -1, and we record the level at which they voted. This is a very interesting line. So I mentioned earlier how big maps are hash tables. However, on Tezos, big maps cannot return their keys. What that means is if you need to iterate your map somehow in a smart contract, you can't do it because you can't get the keys. So what we do is we record the keys separately, which increases our storage cost. And voters, if we go up, is a set of type address. So we're guaranteed that we will have unique elements. Very cool. Finally, we need to be able to count votes and apply the proposal if it passes. So this is something you would have to think about in terms of your own governance process, is what kind of majority, for example, is necessary for adoption of a proposal, or if a submitted proposal doesn't gain at least some threshold of votes, is that considered a spurious proposal and you should punish the proposer for it? So for example, if I submit a proposal to this DAO, nobody votes on it, should I lose my stake token balance just because it sounds like my proposal was ill thought out and I might be a malicious actor? So yeah, definitely things to think about. But going back to counting votes, really easy. We iterate over the list of voters, and remember, this is all Python syntax. Some things are wrapped in the SmartPy library. There are technical reasons why that you can read about in the documentation, but the idea is that some constructs have to be overridden perhaps in Python, and it's just not possible. So we iterate over the voter keys in our voter list, and then we get their vote information from the map. We check if the vote is valid relative to the level that we're at, the block level. And then if the vote direction is greater than 0, it's a yes vote. If the vote direction is less than 0, it's a no vote. And then finally, if there's a simple majority, we apply the name, otherwise nothing. And then we reset the state to allow for the next proposal to proceed. We mentioned earlier this concept of privileged operations. So here we have a set delegate because in Tezos, for the Tezos governance process, you delegate your balance to a baker, to a validator. So this is, of course, a privileged function because we don't want people randomly changing our delegate, our baker. So we check if we have an administrator address that who's sending this request. And again, we added just another element to the settings structure that was not explicitly defined. And then if yes, we set the delegate to that parameter. Withdrawal, again, same thing. People shouldn't randomly be allowed to withdraw. And another thing here, by the way, is we take the balance minus deposits. Why? We do not want even the admin to have the ability to take out user funds because users will want to redeem their tokens back for their balance. But this would allow the admin to withdraw the delegation rewards. And again, about access control, I mentioned earlier that you want to be able to change the administrator. So for example, if I deploy this contract on someone else's behalf, I will then hand it over to them. So I would change administrator. Awesome. Really simple contract. Simple DAO. Now let's talk about testing. Let's actually run these tests and see what we come up with. Right, so we create a bunch of actors who are going to perform operations on this DAO. And these tests really simulate usage as we expect it to happen in real life. So first, these users will acquire a token balance by depositing Tezos, and then they will interact with the contract. So for example, Alice will propose a new name. How? Well, we have the propose entry point, and we know that it takes a name parameter. So we're saying what? We're saying that sender is Alice, because we defined an account as Alice is one of the actors, and we say level 1. So in SmartPy, you can specify time and block level of the simulation. So in this case, we're using levels to measure time passage in a DAO. So we say level 1, next transaction is going to be level 2. It can be level 200, like it can be this, it doesn't matter. But for us, logically, we want to show the next level. So what's going to happen? Alice is going to submit a proposal for a new name. Then Bob is going to submit another one a block later. And we want this to fail, right? Because our logic says that if you have an active proposal, the subsequent one will fail until expiration. Then we want to record votes. So we have some yes votes, we have some no votes, and now we're going to count the tally. We're going to tally votes. So note that the count entry point takes no parameters, and anyone can execute the count, and the count must be executed after the proposal period has expired. So what do we expect to happen here? Oops, I want to do was this. So this is our counts votes. See, this is how it appears. This is really, really cool stuff because you can also see the Mickelson, you can see the Michelin, that's JSON representation of the contract call. And you can see the contract state and how it changes. So this is the contract state after the operation has executed. And as you can see, our name has changed because previously our name is name DAO. Now it's new name. And we have reset the state back to default, and we have our settings. We have admin, duration, this is how long we expect the proposal to take, and the minimum proposal stake. I'm sorry, I missed this point earlier. Right here, we're defining our settings. It's admin.address, which is T address type, duration, which these are implicitly T and stake. So we were talking about type safety earlier, and there are several number types in Tezos. There is int and there is nat, nat being natural number. And note that they're different things. You cannot directly compare an int and a nat because they're different types. So you have to convert one to the other. This seems really simple, but it's a consideration for your code because, again, strict type safety. Cool. So in any case, we had a proposal. A bunch of people voted. Someone tallied the votes, and the DAO performed as expected. The name has changed. Excellent. So now we're going to run through another scenario. Bob is going to again propose a new name at level 35, which is after the contract proposal period. So it's accepted. So if we just scroll down a little bit, we see that some account submitted a function call with a parameter, function propose, parameter name, another name. And we have our current token balances. We have the current name. We now have a new proposal. It expires at block level 67. It's another name. It was proposed by some address. Cool. So now, again, people are going to vote. Let's say Alice is not happy about this name change. So she's going to vote against. And then there'll be a bunch of yes votes. And then at some point, Alice will recognize that she is losing, meaning that here's our vote map. Oh yeah, and these are the voters, right? So we're recording the keys of the big map, as I mentioned earlier. So at some point, Alice recognizes, and this is Alice because she's voting no, that she's losing, right? So there's 10 votes in favor and against her votes against the proposal. So what she will do is increase stake. She will do that by claiming more tokens. So note that our contract balance was 19 Tezos. The contract balance increases 25 and 1 microtez. So now all of a sudden, where's our balances now? There we go. Now all of a sudden, Alice has a higher balance. And then she votes against again to update the vote record from 4 to 10. But it's not just 10, it's 10 and 1 microtest, right? So she is just over simple majority. Then again, some random account, in this case, David, is going to tally the votes and the proposal fails. It fails because, as we can see up here, the most recent vote count was 10 million won against and 10 million even in favor, and the proposal was lost. So this is just an example of how you might use SmartPy to create a system, a smart contract. This is a really simple introduction. SmartPy has many features. It is possible to build complex multi-contract systems using SmartPy. There's a concept of importing other contracts that you can reference them. So there's really a bunch of functionality here that supports software development in a traditional sense, where you have classes, you have inheritance, and so on. And it's definitely worth looking. There are lots of templates that you can take advantage of. As I said before, don't start from nothing. Leverage what people already have. So they have token templates, for example. Other things as well. Yeah, this is all I have for you guys. I don't know if there's going to be a Q&A session. I can stick around for that, but best of luck. Can't wait to see what you guys come up with. Thank you very much.